Hey guys, in this video we are going to continue our review of Statistics 1. Now we're going to talk about different shapes of histograms. So the shape of a histogram tells us how the data is distributed. So here are some common distributions. You might have a uniform distribution where all the data values are more or less around the same. Think of if you were rolling a dice, a single die. You can have the values 1, 2, 3, 4, 5, or 6, and each one would occur theoretically 1/6 of the total times that you roll the dice. It can also be a normal or a bell-shaped curve. You should remember this. This is the one that we're really focused on in this class. Notice some key things about that is it's highest in the middle, it's symmetrical, starts out low, goes steep, peaks off, and then duplicates on the other side. Then you have skewness. You can either have it be skewed to the right or the left, and it might be the opposite of what your brain tells you. You think, skewed to the right, more data values on the right. If it's skewed to the right, there is more data values to the left. And then same for skew to the left. You might think, oh, skew to the left means it's more to the left. No, skew to the left would mean more to the right. And an easy way to remember this is to think of your feet. Left skewed, think left foot. Your left foot has more data values on the right hand side, and your right foot, right skewness, would have more data values to the left. So data to the right has a longer right tail, data to the left has a longer left tail. Finally, a normal distribution has that bell-shaped curve. And again, notice that the mean would be right in the middle. And most of the data values are going to fall close to the mean. So each half represents half the total area. So if this was your mean right here, half of the data values would fall below it, and half would fall above it. The total area under the curve is 100%. That's a very important thing to remember. So if you were to this is a little bit of calculus right here, but even if you didn't take calculus, you could visualize that. If you were to get the area underneath this curve, you would start at around 0, and then you would end around 100%. It'll never actually get to the x-axis in theory, but for all intents and purposes, consider it 1. Areas can be thought of as probabilities, and they can also be written as percentages. Areas can never be greater than 1, nor can it ever be negative. So that's another important thing to note. If you ever get a probability greater than 100%, you're wrong. If your area is ever negative, your probability is ever negative, you're wrong. Other things to note is the empirical rule for data with a bell-shaped curve, that 68% of all data values fall within 1 standard deviation of the mean. 95% of all values fall within 2 standard deviations of the mean. And 99.7% of all values fall within 3 standard deviations of the mean. This graph kind of helps show that. So you have your mean right in the middle, x bar. So 1 standard deviation to the right will be x bar plus 1 standard deviation. And then 1 standard deviation to the left would be your mean minus 1s. So 68% of all the data values fall in this shaded region right here. Then 95% fall within 2 standard deviations. So 2 standard deviations would be your x bar plus 2 standard deviations to the right. And then 2 standard deviations to the left would be your x bar minus 2s. So 4 total standard deviations that is being covered. 95% of the total area falls in this shaded region under the curve between the, I guess that's magenta range. And then same thing for 3 standard deviations has 99.7% of the data falling between that green range right there. So again, let's look at our ages of actors at the time they won an Oscar. So let's say I want to know what percentage of scores are 1 standard deviation away from the mean. Okay, so we have our mean, 44.8. If you reference back to that first video, we just showed you how to get that if you look at one variable statistics. So I'm assuming that you know how to get that and you get 44.7948, but we're just going to say 44.8. Our standard deviation is 10.1 because this is a sample. Since it is a sample, we use S. If it was a total population, we would use sigma. So again, our mean is 44.8 minus 1 standard deviation gives us a value of 34.7. And then for the upper limit of that 1 standard deviation range, you have your mean plus 1 standard deviation. So 34.7 and 54.9. So if you were to look at this right here would be your 44.8 plus 1 standard deviation would be your, what did I say that was, 54.9, and then on the lower limit would be your 34.7 right here. So 34.7, 54.9, and 44.8. So 68% of the data theoretically should fall in that data range. It doesn't have to be exact because you're dealing with a sample. If you had the whole population, it should be closer to a true normal distribution. So let's count. How many data values fall between 34.7 and 54.9? Well, if you counted them all up, 34.7 to 54.9, you would get 26 total people have their age fall between or fall within 1 standard deviation away from the mean. So if you were to put that as a percentage, you would do 26 divided by 39, which is the total number of people that we're looking at, gives you 67%. Let's do the same thing for 2 standard deviations. So we have our mean minus 2 standard deviations. So 44.8 minus 2 times 10.1 gives us 24.6. And plus 2 standard deviations would be 44.8 plus 2 times 10.1 is 65. So 24.6 right here and 65 right here. And we're saying that roughly 95% of all that 39 data values should fall in this range. So let's do our count. If you were to count those all up, really everything would land in that range except for that 76 right here. So we would have 38 total counts within that range. 38 divided by 39 would give us 97% of the data values. So if we were to compare that to a ideal normal curve, that will be our target, we're pretty close. Again, if we had more and more data values, we would get closer and closer to a true normal distribution, but you get the idea. Next is z-score, very important concept. So recall that a z-score is the number of standard deviations a value is away from the mean. A negative z-score means that it is to the left of the mean, so somewhere over here, and a positive z-score is to the right of the mean. So how do you calculate z-score? It is the score, or really just the value that you're interested in, minus the mean divided by the standard deviation. So again, that's the number you're looking at minus the mean divided by the standard deviation. And we're going to round that off to 2 decimal places. So what is this right here saying? Okay, if a z-score is greater than 2 or less than -2, that's considered to be pretty unusual. And then if it's greater than 3 or less than -3, that's really unusual. So where would that look like on here? So anything between 2 and 3 or between positive 2 and 3, that would be considered unusual. I mean, look at how small of a percentage that area is right here. And then anything less than -3 or greater than 3 is very unusual. Look how small that area under the curve would be. So if we calculate the z-score for the highest and the lowest data values, we would have 76, which is our maximum, our oldest dude. I'm not sure which actor that was. So here's your 76. 76 minus 44.8, which is our mean, divided by our standard deviation 10.1 is 3.09. Very unusual. He's the only guy that's within that range. 31 is our youngest guy, or girl. So 31 minus 44.8 divided by your standard deviation would be negative 1.36. Notice that that negative represents, hey, we're to the left of the mean. And this positive is, hey, we're to the right of the mean. And of course, negative 1.36 standard deviations away from the mean, that's not unusual. That would be considered a typical data value. And that concludes this video. Thank you.